And in order to solve this equation, we have to we use the finite difference method to discretize the equation, and then we solve them using the Newton method. As you can see, we don't know the value for the n, but what we did, we first solved it as n equal to 1, which makes the equation linear, and then we used the solution for that linear equation as the initial guess for the nonlinear equation, and we solved it by the Newton method, and then we linearize it by that, and we use the biconjugate gradient method to solve the equation. And then we have these two for the tube side. We assume it's like a kind of like plug flow reactor. It's not the reaction, but these are the equations for the tube side, and we have the same equation for the shell side. So we basically solve for the first grid block, and then we take the result from that and do it for the second. The result for that would be the boundary condition for the second block, and goes on until we reach the end of the membrane. So as you can see here, the continuous line is our experimental data. This dotted line is for order of reaction of 1, so which we initially did, which wasn't matching our experimental data. Sorry, these are the experimental data, the triangle one. And then we tried the different values of n, 1.3 and 1.4. We actually didn't fit these values because we did the preliminary simulation with the single pore method to get this value, and then as you can see here, pretty matches our experimental data. So as you saw in the last graph, at the beginning the permeance doesn't change a lot. So permeance is pretty like constant, and then after a certain point it suddenly drops. And at the same time, the pore size is vice versa. At the beginning, you have a huge drop in the pore size, and then it will like go slower. The reason for that is because at the beginning, you have a big portion of a large pore, which they start decomposing at the beginning. But both molecules of TPS and argon can go through this pores. But then, when the amount of this large pore reduces, then what happens is that even a small change in the pore size will causing the blockage for the argon molecules. So the argon molecules decreases faster. So right here. So even the small change will causing the argon permeance to go down sharply. And then you will get to the point. Let me mention this, that our precursor molecules are bigger than the argon. So at some point, you will get to the point that all the pores are inaccessible to the TPS. So no TPS will go to the pore. So only argon can go through the pore. So that will cause the curve to level off. So because there's no reaction, and then the permeance will get constant. But as I said, not all the pores can be inaccessible to the TPS. A portion of it, which let's say Q, which become inaccessible to the pore, if this amount Q, the portion of the inaccessible pore to the TPS, is larger than the percolation threshold of our network, which for our case is going to be 25%. That means if the 25% of the pores are blocked to TPS, there would be no macroscopic transport of the TPS into the network. So, so if the 25% are blocked, then we won't have any transport of TPS. So as you can see here, we probably have reached the 25% portion of the pores. And we also monitored the pore size distribution during the deposition. As you can see here, the tail, this is at time 0, and then this is at 20,000 seconds, 100,000 and 140,000. As the deposition proceeds, the tail of the pore size distribution will disappear and getting smaller. So that's because you will have less portion of the larger pore. And then we also studied the effect of connectivity of our network. So in order to do that, we remove the, we use this equation. For example, if you want to use the connectivity of the network to be, initially was 6. So if you want to use the connectivity of 5, so we remove the like 1/6 of the network's ports, or make them equal to 0, so no TPS will go on. And then we study we run the simulation for that, and we study the effect of the different connectivity. As you can see, if you have smaller connectivity, the permeance will go down, because what you do is that you also, because you're also making some of the pore size inaccessible to argon as well. So that's why the permeance for the argon is going down as well. So the other thing that we did was to study the effect of the thickness of our membrane. So we let the cross section to be constant, and we increased the length of the membrane from, this is per unit of pore volume, the number, like 30 is going to be equal to 1.6 micron. So we increased the length of the membrane. So as you can see here, as we increase the length, is making the 3-dimensional network look like the 2-dimensional. And when you make it the 2-dimensional, you basically like, in fact, you're decreasing the connectivity of the network. So that's why, again, you will see the drop in the permeance. So finally, I want to summarize my talk. We made a silicon nanoporous membrane by the CVD technique. Pore network model was developed to describe the evolution of the pores during the CVD. The model provides a better understanding of how the characteristic of the membrane structure evolved, and the model prediction is in a good agreement with the experimental data, and we are utilizing this model to optimize the operating condition, and so in order to implement it back to our experiment and make our membrane make membranes with a better performance. So I would like to thank my advisors, Dr. Tsotsis and Dr. Sahimi, and also support of NSF and DOE for this one. So I will take any questions.
Questions?
Yes. You measure?
Do you expect the pore size distribution changes radially in the membrane? Have you ever studied that?
What do you mean? Do you mean in the
Radially through the thickness? Do you have like more smaller pores in the inner shell as you impart towards the outer shell?
Oh, usually the change in the pore size happens in the the beginning of the block that we have, 3D-dimensional block that we have. That means the surface of the membrane. And as you go down, you will see less change in the pore size, because anyway they cannot access through the end. So if the first layer is blocked, then it cannot go all the way to the end.
Are you saying that the pores then will be continuous? You don't have any additional pores? The connectivity that he was talking about, that radially, you just go all the way through?
Oh, I know what you're saying. So you mean in one pore you will have a profile of the, you mean, in one pore you will have a profile of concentration. That means in one pore it will change the pore size as it goes. That's what you mean?
Yeah. Well, one pore would be continuous all the way throughout the thickness, right?
Yeah.
So there won't be any pore size distribution change in one pore going through.
Yeah. But actually it will be, but what we assumed was that we assumed the bottleneck would be the beginning of the pore. So whatever the concentration you have at the beginning of the pore, you can assume the rest is the same thing. So, but eventually you will have like slope shape of the concentration profile, but you can assume everything is the same, because the bottleneck is the beginning of the pore.
All right, well, we're running out of time. Let's take one
question.
Oh, one more.
The title is nano.
Yeah.
Any measurements on the nano scale?
Yeah, basically our supports are nanoporous. The average pore size is 65 nanometer, and then as you can see, the pore size decreases. The simulation shows that it goes down to like 0.8 nanometer in the pore size, average pore size at the end of the deposition.
Yeah, let's think, right?
Look at that.